I was hoping in this brief 45-minute talk or so, I would try to shed light on this word technology, because somehow quantum mechanics and technology going together really talks to me about a new era in the definition of this theory. So in fact, I would like to start off with this particular image. If your pointer is working. There we go. Oh, there we go. Yeah, it's on. Yeah, it's on. Okay. Got it. So this is a very traditional image that you have from the 5th Solvay conference, colored after the fact, of course. And you see many of the proponents of quantum theory, and of course, you see Marie Curie, 2-time Nobel Prize winner in the front here. What was quite amazing is that at that time, if you like, this discussion was, does entanglement actually exist? In fact, or is it a mathematical artifact of a theory that you need to explain something under the world? And this continued between Einstein and Bohr. And I have to really pay homage to this book by Manjit Kumar because I love the tagline that says, you know, Einstein and Bohr and the great debate about the nature of reality. And somehow I think what's amazing is that this is now turning into an engineering resource. So the talk today really talks about the necessity still of fundamental science to understand where quantum is going and what are the new generation of science problems that will really fuel the technological revolution, and looking at where we are now and what are still outstanding challenges in the field. So to summarize, the basic premise is that our observations of the world only reflect some aspects of a much more complex hidden reality. So the quantum world below the surface is entangled. And we only have a slice with our observations of that particular complexity. Is it really true? Well, we need this underlying structure to explain basic observations, even though we cannot directly measure it. And there was a century of trying to find other theories to explain that. And really, with the era of Bell after that, I think we settled on entanglement as the answer for the moment. So we are now really entering an era where we can finally use the quantum nature of matter as an engineering resource. And this is tremendously exciting and puts together a new set of fundamental questions of how to take a theory, how to take a mathematics of entanglement to something you can buy and use. I think you know that the technology is moving forward when The Economist writes many articles on it, and in particular has the tagline, "A mind-bending technology goes mainstream." And if you like, from this BCG group report, which is very thorough, it says what happens when the if turns to when in quantum computing. So folks that are thinking about investing or where this technology is going, you can see the growth really in terms of many billions of dollars, both in the private sector and also in academia, thinking about what is the promise of quantum. And you see charts like this. What are the things that you could do if you had a quantum computer? And then I want to bring this a little bit back to reality of perhaps what we can do today and how to actually go here. The general idea is that if you can solve certain mathematics problems more efficiently using quantum mechanics, then all of this mathematics, which powers simulation in various industries, optimization of finance portfolios, machine learning, cryptography, all of these things would be accelerated. But in fact, we are quite some distance away from this. And in fact, getting a quantum technology to outperform a classical one is a very delicate task. So in fact, I will talk a little bit about that and whet your appetite about perhaps what's more realistic in the very near future and how do we actually get here. That being said, I do want to pick one of these problems in chemistry. There has been quite a lot of discussion of how to use quantum algorithms to find the ground state of complex molecules. And one can think about then how to use that information for designing a drug, say. And that problem turns out to be actually a very hard one. If your molecule size is large, both classical and quantum resources will have to be large. And we are unable to do that for a large molecule. But there may be some interesting things that we can do along the way. So what I'd like to show you is the following. If you look at the economics of how a drug is selected these days, it takes about $2.5 billion to identify a new drug. Okay? And the way this works is that preclinical research selects 0.1% of small molecules for trial. And then 10% of these clinical trials are successful. So it's not a very high success rate proposition for looking at drug discovery. And the problem is that quantum effects and molecules evade classical simulation. So even if your quantum computer didn't solve the precise structure of the ground state, if you improve this 0.1% to 1%, there would be a 10 times improvement on a very large number. So there's a lot of things that quantum may be able to do along the way. So we, like others, have participated in trying to solve for chemical structure using quantum mechanical results, using both classical and quantum resources, but we should perhaps broaden our minds in the near term, thinking about other information that we can get from quantum-guided technologies. Just to give you a sense that there may be things along the way that you can pick up before a full quantum computer is available. In this particular section, I want to talk about the difference between 1 qubit and a quantum processor. Those two things are very different ideas. And in particular, quantum mechanics brings in the idea of your quantum system and the environment. And both of those things are critical to understand what's happening in a quantum system. So let's start with NMR. If you've gone into one of these machines to have your MRI, then typically you're looking at the polarization of hydrogen atoms. These are water molecules that are there. You apply a magnetic field to quantize the axis of your spin. And of course, a measurement in this basis will always give you up or down. Okay? You will either measure red or blue in this case. You prepare a 50-50 superposition, say in green. Half of the time you measure up, half of the time you measure down. This is typically represented on a sphere where the two poles will give you the red and blue states that are there. So with this 50-50, you get a sense that, in fact, the spin can point anywhere. However, your measurement is decimating your results to be aligned or anti-aligned with an axis. So the complexity underneath the surface is much bigger. So in NMR, we are taking advantage of this quantum property, but you're looking at it at an ensemble sense. You're not measuring typically the response of one water molecule. You're looking at the response of a piece of tissue or a tumor or something else you want to look. And we use that nomenclature of T1 and T2 to tell you about the decay of that particular quantum state. So the challenge really of quantum computing is to take this NMR, if you like, in this language, and put controls on it at the single molecule level. And in fact, these NMR type of quantum computers were used very much so in the early day, even when demonstrating factorization of numbers by Shor's algorithm. Okay? This conference has also a flavor of quantum materials. So I wanted to go ahead and contrast these fields that we term in modern day as quantum materials and quantum information science. The field of quantum materials, if you like, which has two-dimensional materials or complex three-dimensional structures, looks at quantum effects where the experimentalist is assisting or encouraging nature to assemble complex structures. We have some complex synthesis mechanism to come up with, let's say, a superconductor, whether it's YBCO or an iron-based superconductor, or a van der Waals material in 2D or the like. And this quantum coherence, then, is preserved by structural perfection and symmetry. You'd like to get the best possible crystal so that you can look at this emergent phenomena, which is quantum coming out of this. Typically, there are no wires in this setup. You're not addressing the individual unit cells that are there. So the effort to build a quantum processor is really a complete redesign and synthesis of quantum matter. We are picking the crystal structure that your qubit should take. How should they be connected? Nearest neighbor, tetragonal, in a ring, or what have you. And that's very different than encouraging nature to protect quantum coherence. By definition, we are going to break the symmetry of that material because you need to get signals in and out. Okay? That's a very different proposition, of course, than trying to preserve the coherence inside. And moreover, not only do you need to get information in and out, you need to change dynamically the couplings in your setup. Certain elements need to talk to other elements at a different period of time. So it's not a static problem. So you see, these two things, they share quantum in their name. And of course, there is coherence involved. But in fact, the regime, whether it's open or closed quantum system, is very different in these two cases. With that, you have the following flora of different qubit technologies. Whether they go from some very microscopic technology, such as an electron in a quantum dot, or a vacancy in diamond, to a single photon, to a single ion, or circuits that have superconducting circuits that have common behavior, that's quantum, or in this beautiful talk that we heard from Professor Wiesendanger, where we can have, in fact, Majorana modes in certain semiconductor structures. I should put your pictures here now, after that beautiful talk. So what's the winner? That's the usual question the DOE will ask me, which one should we do? And the question is, it's a loaded question for the following reason. When you're building, as I said, a quantum information system, you must have wires to the outside world. So your quantum system is the qubit and the environment. And this plot is only showing you the qubit. I have said nothing about the environment. So you have the choice here of taking systems that naturally decouple from the outside environment, or systems which couple very strongly to it. So you may say, well, let's always pick the ones that decouple from the environment, because you will get maximum coherence. The problem is we are also part of the environment. Right? The environment has two pieces. It has the experimenter getting information in and out, and then it has the other people that you don't want to get the information that's there. So in these systems, if you are looking at a very open quantum system, like a simple superconducting circuit, the name of the game is to suppress all the bad actors and then get the information for yourself. If you are working with a system with topological protection, then the name of the game is to allow you to have access to the information. None of those problems are easy. So I think that point is that we have not picked a winner yet. And in fact, the real technology may involve all of these. Because after all, your computer may have a memory, your computer may have a processor, it may have links for transduction, so on and so forth. So there's a lot of fundamental science before we sort of pick on the quantum computer. So with all of those words, let me start talking about superconducting qubits. This is a zoom in of a typical superconducting device that we make. We have our own class 10 clean room. We produce superconducting wafer scale qubits in 2 days or so. So here is an example, a zoom in of a certain plaquette with qubits shown here and resonant structures linking them. The materials are niobium for the golden colored stuff. The tunnel junctions are aluminum, which is there. I'm glad you also like niobium. So the premise that brought a lot of us into this is why use a superconductor? The general idea is that you pair excitations into Cooper pairs. This allows, at least for DC transport, to be dissipation free, and you also have the Meissner effect in a big crystal. To be honest, almost none of these things are exactly relevant for superconducting chips, because in fact what's happening is that you have surfaces. And in AC properties, the surfaces and interfaces matter. Right? If you have, for example, a dielectric on top of your surface, then that will also couple inductively noise into your system. Whereas for a DC current, you could pass it, of course, in parallel. So I'll show you a few images about what's happening on that niobium surface. Right? And there's a lot of physics to be learned just by looking at surfaces and interfaces. In addition to that, we have this nonlinear elements called Josephson junctions. And what's happening in the tunnel barrier of Josephson junctions is another saga in and of itself. So I'll spend some words on that. And moreover, once you start putting in wires, then you have additional many-body noise mechanisms that are there. And what I want to end up with is to show you that if you start to learn something about the noise, you can get a lot more computing power out of your quantum computer. So with that, going into experimental data, this is the group on campus that I'm very thankful for. We'll talk about their results. The whole group can be seen on these two websites that are here, which include collaborators at Lawrence Berkeley Lab, the Molecular Foundry, and the National Center for Electron Microscopy. Superconducting qubits is basically an LC oscillator. So we start off with a very simple LC oscillator. This is the mechanical analog of a harmonic oscillator. Okay. In a harmonic oscillator, all the energies classically are allowed. If you quantize it, then only certain energies are allowed. but they are all equally spaced in energy, all by h bar omega. If you'd like to turn this into a quantum information system where you can address, let's say, a certain pair of levels, we need to have nonlinearity in the system. So for that, we put in a Josephson tunnel junction into the story here. Okay? So this is an aluminum oxide, aluminum tunnel junction, which creates an unequal set of energy levels with spacing somewhere between 1 and 10 gigahertz. If you're a theorist, you can think of this as a particle in a cosine box. That's the end of the story for a Josephson qubit of this particular flavor. This type of qubit is very open to the environment. It couples to many types of defects. You can have amorphous dielectrics shown here. That's all the fuzzy stuff on top of these metallic films and also at interfaces. You can also deviate from this nice picture of Cooper paired excitations into quasi-particle excitations that are there. And you have also very interesting things which remain yet a mystery. Noise sources which have a 1 over f distribution. So flux noise, for example, is a very well-known old problem. If you make a ring and look at the flux through it, you will see fluctuations of this 1 over f type. And of course, this leads to decoherence in different methodologies, which I'll talk about in a second. Okay. Let's start looking at that niobium surface, okay, in particular after we process those wires. So here is a microwave structure. This is niobium sitting on silicon. And the niobium surface here, you can see there's the niobium metal, and then there's this yellow stuff on top, which I call NBOX, telling you that we have, in fact, all the different stoichiometric combinations of niobium oxide that are there. So this is a high-resolution transmission electron microscope. If you now go ahead and do XPS on this, scattering measurements, you will see which parts are NBO, which parts are NBO2, and which parts are NB205. Okay. And they give decoherence in different ways. Some are semi-metallic, some in fact are reasonable insulators, so on and so forth. And this color map tells you that we have a lot of NB205, a particularly bad actor in this game. You can do the same with the silicon surface. Here's silicon and here's SiOX, telling you the different oxidation states of silicon that are also there. The niobium silicon substrate actually is quite good for us. You can see almost all those crystallographic planes. So that turns out to be a pretty clean interface. So the niobium silicon interface is very clean. We observe multiple oxidation states of both niobium and silicon. And as we start to peel away these layers, we can figure out which are the ones that are really messing up your coherence in the system. So in this case, we've made resonators, and we're measuring the quality factor of resonators with different etching techniques where we remove these oxide layers. So the quality factor here is expressed as a loss tangent in part per million. More loss, lower coherence. That's there. You start off with an oxide of order 5 nanometer thickness, and you start to etch it down with a particular cocktail of acids to remove this. And you can see the loss tangent is dramatically different. In fact, we are able to go from 1 million single photon Q to 10 million single photon Q at wafer scale. So just by removing a few nanometers of this NB205. What's also very interesting is that in this etch, we haven't actually passivated the surface. So you would imagine the stuff would regrow. But what grows back is different than what you prepared the first time, saying that by changing the kinetics of the chemistry, you can change which flavor of niobium oxide you get. So there's a lot of subtle surface physics that comes into actually improving the quality of these films. Moreover, this NB205 is a very interesting compound. It, of course, is paramagnetic as a crystal. However, when you put it on a surface, like the surface of niobium, it's lattice mismatched. And that lattice mismatch can actually introduce magnetism into it. So we'll actually get a little bit of a magnetic moment. And if you start to think about flux noise, you can add one more character into that list and saying, is it really the NB205 under strain which is fluctuating? Don't know, but interesting question to look at for flux noise. The typical story with a lot of these defects starts with the usual physicist model of saying that we really don't understand what are the defects. So we call them under this heading of two-level system. What is this exact two-level system? This is a matter of debate. The general idea is that you have some double well potential that can correspond to two different electronic states. Maybe it's the bonds on your surface which are rotating. Maybe it's a charge which is going from two other places. Maybe even more sophisticated things where quasi-particles, as Professor Ustinov and others have shown, really correspond to an effective two-level system. We don't know. This is sort of some very generic model. It was so generic it went away. So this is some very generic model of two-level systems that are there. And in particular, I want to pay homage to this very beautiful experiment of Professor Ustinov, who's here and will be speaking later, where these two-level systems are thought to have both an electronic component, so they couple electronically to your qubit, but if they're structural, they should also couple to the strain field. So typically, we don't have a handle on the two-level system. We're measuring electronically these superconducting circuits. But in this experiment, they literally put, figuratively and literally, a screw on the problem to go ahead and add strain to the system and actually sweep the two-level system. And the spectroscopy of that is exceptionally rich, beautiful, or messy, depending on which side of the problem you want to look at. So there's a lot of two-level systems, and they even interact with each other. So again, another whole genre of physics to try to understand what are these systems, how do they interact, and in fact, how do we get rid of them or passivate them to improve these qubits which like to talk to the outside world. Then there's the junction. You see, the junction inside also has dielectric materials. In this case, we're looking at aluminum, aluminum oxide, aluminum. And if you think about the material inside, perhaps one of the reasons we have not been troubled by this yet is that it's really small. Right? These are sub-100 nanometer junctions. If you do the estimation of at what level of coherence will we be plagued by the Josephson junction, we're starting to get there. As you start to remove the oxide from the outer surfaces, the junction starts to matter. And if we have, let's say, a few hundred microseconds of coherence time today, to exceed some milliseconds, we will have to pay attention to the Josephson junction inside. So this is where it's a very long file I've clicked. So I'm in the queue while the computer updates. And I'm supposed to make, it did it. Otherwise, I was going to make jokes until the next slide updated. So here's a high-resolution TEM of that cross-section of a Josephson junction. It's quite an exquisite picture taken by the LBL folks that work on this National Center for Electron Microscopy. You can see all the different grain edges there of the little chunks in the aluminum piece. And you can see that little sandwich layer of aluminum oxide in between. It's not flat, it's not uniform, it's not pretty, but it's worked for 50 years. And part of that is because these junctions are very spongy. You can go ahead and take out the strain by having this amorphous layer. So on average, they give you a very uniform tunnel current. If you start to look about fluctuations, that story may be very different, right, in these. Moreover, we can go ahead and take a scan. So here's a zoom in. That's the 10 nanometer scale bar there. You can now go ahead and zoom in on this barrier and look by chemical analysis or scattering analysis how much oxygen and aluminum you have as you go across some region of the barrier. And it changes a lot. So in fact, how does that play into the performance of your qubit will still be an important issue to look at. Okay. So enough about materials. What I'd like to do is tell you about how to go beyond this very simple circuit. This circuit here, again, is the Josephson junction capacitor piece. And there are really three energy scales in this circuit. There's the energy you store in the capacitance, either the linear one or the one in your junction, and the energy you store in the inductance, which is divided between the kinetic inductance of the junction and the magnetic inductance of your inductor. So that qubit that I showed you that was just an L and a C, roughly speaking, goes into the name of transmon. There are other qubits in this family where I can change the ratios of L and C. And they may become more or less resilient to noise that you have. That's not building in topology into your Majorana modes. That's just using parameters which are more favorable for a given setup. But you could start to build in topology into this system. So the typical Josephson junction has 2 pi periodicity. You can start to look for systems that have pi periodicity, in which case you would have 2 ground state solutions as a function of the phase difference across the junction. That would allow you to protect more accurately your information from the outside world. And how do you do that? This is the original proposal by Brooks, Kitaev, Preskill for looking at something that was called the 0 pi qubit. So walk you through a little bit of this picture. There's a Josephson junction, there's an inductor, there's a capacitor, but then you have another rail of a Josephson junction, inductor, and capacitor. What's happening here is that you have Cooper pairs that are transiting across this junction. You have Cooper pairs that are transiting across the bottom junction. What's interesting is you can actually correlate their behavior and you make kind of an exciton, where you have Cooper pairs on the top and Cooper pairs on the bottom, right? And they track each other. And if you pick this capacitor and inductor correctly, they will not go from the top layer to the bottom layer. So effectively, you have now created a circuit where you are not looking at the transport of Cooper pairs, but the transport of pairs of Cooper pairs. And you can do the same with fluxons, where you have not one fluxon, but pairs of fluxons. This device, of course, has 4 terminals, so it's not exactly your 2-terminal qubit, so you just fold it together, connecting 2 of the phases, and you get a 0 pi qubit. Okay. So just to show you, if you want to increase the complexity of the number of junctions you use, you can start to get things which are more protected. And there's an entire zoo of circuits to look at, and this is an active area of research. Okay. So in the last 10 minutes of the talk, I want to talk about noise. Professor Wiesendanger showed us this nice plot of quantum volume, saying how big is your Hilbert space. You can think about it this way. If you have 10 qubits, you program something in 1, by the time you get to 10, number 1 may forget. Right? So you have not created that full size of Hilbert space that you need. So we have to think about what noise is really present, right? And what can we do about this noise for more intelligent solutions at error correction or noise mitigation. Okay. So we can have a long discussion of the mathematics of noise, but I will try to use my arm as the olive branch, if you like, to make this a bit easier. So typically for the experts, you write out an error channel in terms of polymatrix, so you figure out where the errors are, whether they're errors in the x rotation, y rotation, or z rotation of your qubit. But here's a very simple way to look about it. If you have a 2-level system that you can parameterize on the surface of a sphere, that's basically represented by a vector like my arm here. Okay? If that vector jitters, so you see I'm jittering my arm like this, then if you average all of those together, it appears as if the average length decreases. Right? So in fact, I'm going ahead jittering this around and the length decreases. That's called depolarizing noise. And what I've done is I've introduced an error channel equally along x, y, and z. Okay? So the statistical average of that is a vector which is smaller. You can have a particular noise where you do this only in the xy plane. That's typically dephasing, because you're messing around with the angle on the plane. And then you have this type of noise, which is particularly nasty. Right? And only recently, I think, we've become very aware of this. The dephasing also causes this kind of perturbation, but only along x and y, because it's not the z which is changing. This error is called a coherent error. So I have, for example, my hand, and I try to make it point this way, but I mess up, it points this way. Okay, so I have an angular deviation. Well, you may say that's not really an error, right? It means I just missed the target. It's not as if I've shrunk the block vector, and that's absolutely right. So for a long time, we thought we were dominated by T1 and T2, which is this random fluctuation that reduce your noise. But in fact, it turns out you have a lot of this noise. This noise is actually much worse for running a quantum circuit than this one, for the following reason. If you have random fluctuations, you average away, and they scale as square root of n, the number of fluctuations. If you have an angle, it just concatenates, right? And your arrow points very far away from your original state. And if you could stop that noise or change it, you can run much more complex quantum algorithms. And that's what I want to show you in the last few minutes of the talk. Oops. So what's the difference? Coherent errors, they really represent, if you like, imperfect unitary operations. You would like to do a rotation, but you kind of mess up. You get the angle wrong, you get the axis wrong, so on and so forth. They maintain quantum coherence. It's not as if you've lost your quantum state. It's just a different quantum state than the one you wanted. They can be constructive or destructive. Maybe you get lucky, and somehow those angles add up in a way that they cancel. Okay. So very difficult to predict, and they have a quadratic impact on accuracy. Stochastic interactions with a noisy environment, such as pure dephasing, they do not maintain quantum coherence. So your vector is shrinking. Information is lost to the bath. You cannot get that back. Okay. So you may think that's really bad, but in fact, they only have a linear impact in their scaling. So the real question is, which one do you have? How do you check, in your quantum processor? So that story starts with this technique called randomized benchmarking. Okay. Randomized benchmarking says you prepare a state, run it through some set of gates, undo them, and see what you get. So let me go ahead and sort of demonstrate with my hand again. I start with this state, okay? I want to rotate 90, 90, 90, 90, 90, right? And come back to this state. So that's the sequence. If I have a little bit of noise, I miss, and I'm just a little bit off, right? And the amount that I'm off by tells me the error. That's the idea of randomized benchmarking. You go through all the gates and see how far you are off on average. Okay. So you repeat this, you fit a decay to this, and you get a total error rate. However, this only tells you about this kind of stochastic error because you're averaging the rates. You're not really figuring out whether you have this misrotation or just some stochastic noise. It doesn't tell you that. What you can do is at the end of this randomized benchmarking sequence, measure the length of your block vector. And that will tell you not only how much have you deviated, but how much has the vector shrunk. So that gives you a sense of what's the balance between these two errors. So if you look at here, for 1 qubit gates, the total error rate is 10 to the minus 3. That's what you were indicating on your plot, right? And the coherent error rate is almost the dominant error in there. So that's a significant source of error. It's not the stochastic noise that's there. And if you run 2 qubit gates on pairs of qubits, the same story. The overall error is bigger, but it's dominated by this kind of coherent error. So how do you get rid of this? Or how do you turn some of this coherent error into stochastic error? Let's go back to this picture. I wanted to hit this point here, but every time I do it, I miss. Right? That was the picture I gave you. So on average, it looks like this. The vector is shrunk. The idea is, can I now go ahead and prepare an algorithm where I add some degree of randomization to stop the accumulation of errors? So in this notation, you have 5 qubits, say. They're going to run these particular gates, no matter what they are, X gates, Hadamard gates, etc. And what I'm going to do is I'm going to add random rotations in between. So what this does, it stops the accumulation of this coherent error. They're no longer correlated as you go through. And you may ask, well, this is going to make the circuit more complicated. Actually, it doesn't, because I can recompile those into the original rotations. So before I showed you a circuit 90, 90, 90. Now I'll do 92, 93, 87. So adding that little randomization kills the coherent error, or should kill it. Right? And in fact, this is experimental data showing you that we really are dominated by these coherent errors. Right? And in fact, if I now randomize even 10 times, this is the error budget which is there. The yellow is the coherent error, the yellow is the stochastic error, the blue is the coherent error. And you can see the original budget had coherent error much higher than the stochastic one, but after randomizing, I can take that coherent error to 0. And in fact, make it dominated by stochastic noise. And I can do that for actually any 2 qubit gates if you want, not just the one that I've shown here. So it's generally a useful technique. So the final piece of this is, can I run an algorithm that I couldn't run before by using this randomization? And the answer is definitely yes. So let me show you that in the last few minutes, and then stop for questions. This is a popular algorithm which has come out. It's called the quantum imaginary time evolution algorithm. So the general idea is, as we know in quantum mechanics, if you have a state, you evolve it as a function of eigenstates that have some simple time dependence e to the minus iet over h bar. So those are the eigenvalues that cause your state to move forward in time. How do you find the E sub m? That's the hard problem, right? The spectrum of eigenvalues that are there. If you go ahead and turn time to imaginary time, it looks strange, but it works. Right? If you turn this time to imaginary time, that exponential then becomes a decaying one. Right? And in fact, depending on the size of your eigenvalue, you will decay either faster or slower. And in fact, the ground state is the one that will decay the slowest. That's the smallest exponential that's there. So if you classically, you do a simulation, you just wait and see what the computer returns after a long period of time. That's the ground state. Quantum mechanically, you have a problem because this evolution is not unitary. So you cannot map it directly onto a quantum computer. So the best you can do is break it up into little chunks, and that in the field is known as a Trotter expansion. So you just think of little unitary chunks for doing this. And you can go ahead and see if you can obtain the ground state. So here in a snapshot, we've actually solved the 3-qubit transverse-field Ising model for where the coefficients between this H and J are 1. That's the hard limit of this particular Hamiltonian. The green curve, represents no error mitigation, no randomization, etc. And what's plotted here is the average energy error and the error in the estimation of the state. So here I'm measuring the eigenvalue, here I'm measuring the eigenstate. And you see this line here, this is of order 1. So the average energy error is of order 1. You really get it wrong, right? We can't actually run that algorithm. And the same with the state. But after you go ahead and turn these coherent errors into stochastic ones, you can see I can bring it down to almost 10 minus 3 for chemical accuracy. Just by changing the noise in the system. I haven't done anything with the qubit. I'm just saying that I don't want to accumulate all these errors when I'm running 50 C0 gates or 40 C0 gates, which would give me a trash answer after running 50 operations. Pick a very different problem. You can now do a simulation of nuclear collisions, where I go ahead and think about two nuclei interacting with the following Feynman diagrams that have a spin-independent and spin-dependent piece. So that evolution, again, same story. You can write as some kind of Hamiltonian here that has two pieces, and you try to estimate one of them, okay, by this quantum methodology. And here's the circuit. It's got a lot of stuff. It's got each unit cell has 3 C0, a bunch of rotations, so on and so forth. You run it without error mitigation, no hope to actually get any answer at the end. So here the scattering cross-section of the 4 states that you should get in a nuclear deuteron scattering problem. And what you see here are the lines, in fact, are the simple exact calculation for this quantum system. The dots represent what we get out of the quantum computer. Original data, no mitigation, way off from what you predict, and this is the error. And as you start to randomize it and then adjust the length of your state, etc., this is the quality of data that you get at the end, right? Just by adjusting the noise in your quantum simulation. So again, showing you it's quite important to understand the type of noise and many-body noise you have to do not only error mitigation, but as you were mentioning, to really think about how to correct in a fault-tolerant manner errors and how to characterize them. So in my last slide, I think I want to leave you yet again with a philosophical outlook. So where are we in quantum computing? I would compare that to a journey through the Alps. And these are some photographs I took of Mont Blanc last time there before COVID. So the first processors, we were planning the route. The summit is somewhere over there. You see all these people looking there saying, how the hell do I bridge this gap? Right? That's sort of what we're thinking also with quantum computing. How do I bridge that gap? Okay, so we start to develop tools, control quanta, and then you get closer. There's always clouds. You don't always see the rock face. Sometimes they clear up. You start to see the rock face, which is there. And if you like, this is the first quantum systems to exceed classical resources. We start to get a sense that you could do something. And then the real advantage will be to actually reach the summit, where you can make a quantum computer do something, right, that a classical computer cannot. And that's the development of error management, robust devices, error correction, impactful algorithms. But the thought I want to leave you with is it the end of the story? If you fixed the vacuum tube, would you know what the transistor would turn into and what metaverse or Facebook would look like 40 years later? Probably not. And if you cross to the other side of the Alps, that's the Italian town of Cormeyer on the backside. So you have no idea that that's what's on there on the backside. So what I want to leave you with is maybe the best of quantum still yet to come, figuring out what you can do with this technology. And to get there, we really need to think about new modalities for robust encoding of information so that you can access it and hide it on demand. Development of systems level engineering, not just one qubit, but in fact, how does a many-body system interact? And engineering which is targeted for quantum-specific solutions, for wiring, for data transfer, etc. And then also to rethink about the right algorithms for the hardware you come up with. So let me stop there and take your questions, and thank you for your attention.
Thank you, Professor Siddiqi, for the excellent presentation. If I may ask, what is the main source of the, the coherent errors? I mean, XYZ axis errors, they could be due to, gate measurement errors or, gate operation errors. But what is the major source of the
crosstalk?
Crosstalk between the qubits.
Crosstalk comes in two flavors. There's classical crosstalk and quantum crosstalk. So the classical crosstalk is that you want to control one qubit, but since your wavelength is bigger, you are not in the you're in the near field regime of your microwaves. So in fact, through coupling, through dielectrics, etc., you will excite some other qubits. And that happens in some n-body fashion. And in fact, we can decompose that into all the n-body correlators, like condensed matter physics, and figure out where's the two-body correlator, three-body correlator. So that's what happens on the classical crosstalk.
Yeah.
The quantum crosstalk, even more subtle, right? Because in fact, these are dipoles, so you will always have a dipolar coupling, right? A ZZ coupling that's there. So you can kill that dipolar coupling in many ways. You can try to come up with not just a capacitor coupling it, but a capacitor and inductor, which has the opposite sign. So crosstalk comes in all different flavors, and that's what gives you many-body errors typically that are there. And going in 3 dimensions also helps with that.
Yeah. Photonic qubits, I think, in that respect, right? Crosstalk, they wouldn't have crosstalk or kind of errors. You know, they would have only XYZ measurement errors, right? It seems.
Right. So from the point of view of crosstalk, they're better, but then they're difficulty there from the point of view of talk, right? Then they don't talk to each other. So you can choke off the complete channel, but then they have no.
And there are some ways, you know, to have like CNOT gates, right? In between.
You can do cluster states. You can do cluster states. You can feed forward. You can bring in the nonlinearity from the measurement, right? That's there, and then your measurement will have crosstalk. So it's a challenging problem to get an extant array of quantum entanglement to be controlled on demand without looking at it.
Thank you. Any questions?
First of all, thank you for a marvelous talk.
Dankeschön.
I have a question. Do you have an understanding at a microscopic level why the aluminum-based transverse tunnel junction perform better than the niobium-based tunnel junctions? It would be a natural choice also for the tunnel junctions to use niobium. Do you understand why there is a difference, say, in the performance, and what makes the niobium-based junctions worse?
So understand is a strong word, so I will share some thoughts on that particular subject. Typically, niobium junctions that are made still use aluminum oxide. So when you make niobium tunnel junctions, you grow a very thin layer of aluminum that's proximatized by the niobium, then put aluminum oxide, and then grow the niobium counterelectrode. Those junctions can be made to have high coherence. The Lincoln Labs folks have done that. So that's maybe the first answer. They can perform as well. If you want to make a junction purely of niobium with the niobium oxide, it's a surface chemistry problem in all of these things. Whether you use rhenium or aluminum rhenium or van der Waals materials as your thing, or boron nitride, or any of these other materials, it's the dissipation of that material, the interfacial transparency, and the stiffness. And that's typically one of the biggest problems in epitaxially grown junctions. You grow a very thin layer, the transparency is very high, right? So if you have even one channel go bad, then your junction is short, right? So that's one problem that's there, especially as you cool it down, because you will be lattice mismatch in typically all of these substrates. The second challenge then, of course, is do you want it to behave properly on average or each element? Right? So in this particular case, this is in this Landau-Buedeker formula, the case of many channels with poor transparency. So on average, it seems to work. If you want to go to the limit of either a wire or a point contact or something that has high transparency, then you have to deal with this channel fluctuation problem.
Okay, thank you.
Okay, we had another question right there.
Okay, I guess it's me. I have 2 questions. One is that I guess for the beautiful algorithm at the end, somehow the algorithm is known. There is some sort of a compiler or something that adds these other gates. Is it kind of theoretically known how good that can be? Because you're trying to get an inverse, but there is no inverse. Yes. So, but is there like an approximate theory to say how close can we get?
Yes, it's a very good question, right? Of things that how close to the, if you sort of have this kind of quantum approximation to things that are classical. There is a good theory for this. Turns out I think you can get, at least in that particular algorithm, you can get to better than 10 minus 3, which is good enough for operational purposes. But it depends on the structure of the interactions that you want to look at. So if you have, for example, a many-body Hamiltonian with many levels of interaction, it's not so obvious, right? So it depends on how you want to fracture that circuit. That's the first question. You have 2. Right?
Okay, yeah. The second one is when we talked about niobium 2, oxygen 5.
Yeah.
What is the participation ratio? Does it matter really? Or what level we are looking at?
So that picture, if I go back to it, see if I do this and hold it down, how fast it goes. Not very fast. So if you look at it, we're talking about 3 nanometers on a 5 nanometer oxide layer on top. So that's basically the amount. Oops.
Yeah, but from microwave perspective, how
Oh,
much
it
are they
matters a lot.
contributing?
In fact, it's dominant, because the point is you want to create a circuit of loss 10 minus 6, and you put a material of loss 10 minus 2. So it is the dominant.
But is it participating enough? I guess that's
Yeah.
okay.
Absolutely, because what's happening here, you can use this one. The electric field is concentrated right there on the top. So in fact, it is maximally participating in that. And what's participating even more is the silicon here, because it's between the electrodes.
Yeah,
So
yeah.
absolutely.
Thank you.
Question here.
Any other questions? There's one over there. Okay.
When I was little, in kindergarten, the onties, as we call them, had a very neat way of suppressing our random fluctuations. And this was whenever we went anywhere, they told us to hold hands. Okay, so my question is, can you somehow have two qubits, one monitoring the other, a sort of coupled state that would then tell you if they are drifting?
Yes, it's a very good question. So in fact, it's this entire subject of how to encode information in more robust states that are there. So in this case, if you have a dimer, right, they would actually go ahead and either, you can use them as one as a sensor of the other, or one to co-scatter. Yes, so both of these things are being done at the moment. One of the things we do is cheating a little bit, but maybe useful. We hold hands in a different way. You can have this transmon with 3 levels, right, and use the 3rd level as a sensor. So you're holding hands with yourself. So yes, so you can try to correlate these and also try to correct for them, and you can do continuous error correction, which I didn't talk about today, but that's something with continuous quantum monitoring you can undo. So yes, all of these things I think are important, either autonomous or with feedback. So autonomous meaning you hold hands but don't look. Feedback, you hold hands and measure and then do something.
Okay, Professor Gencer.
Thank you very much for the nice review and the current achievements you have already. Very simple and short question. What is the current state of prototypes by IBM, Google, and they're using aluminum oxide junctions? Yes. I mean, what would be the advantage of this and disadvantage? Have you had any chance to make a comparison?
Sure. So the question, of course, to restate it is, how do you compare, for example, this architecture or other architectures within the superconducting field? The point is, I think that there are many good solutions that are out there, and all of them are some distance away from the final product. So if you take this problem of transmons, right, then we need to make really perfect surfaces, interface, qubits, wires, so on and so forth. And that is really the approach that much of industry is taking. They're all typically working with transmon qubits. It is a very engineerable approach. You agree on the structure and go ahead and I want to improve the quality, and you have lots of benchmarks and metrics. So what I was taking is perhaps more of a professorial approach, saying that maybe we want to change the target, right, and look at some other targets that are there. And it's not obvious which one will be better. So I think there are all approaches which are working in parallel. We already had one comment on error correction and the difficulty of it. So all the commercial entities are doing surface code error correction, typically, which will require many, many 100,000 qubits for encoding. So whether it's easier to come up with a better code or a better qubit remains to be seen. That was the most political answer, Professor Gencer, I could give you about the state of the field between all entities working in it. Tonight with the Turkish night, I give you the real answer.
Any more? No. Okay.
Thank you again. Thank you. Teşekkür ederiz.
Hopefully see you next week.